Hello and welcome to Math251, Calculus Online, here at Cañada College. My name is Lapuz. In this video, we will take a quick preview of Chapter 2. Chapter 2 covers limits and derivatives, starting with the idea of tangents and velocities. We will approach these problems with limits and continuity until we apply limits to the idea of the derivative. The first section gives us an overview of these problems. We may have been taught that the tangent line passes through a graph at exactly one point. This definition is not clear as there are many such lines. More precisely, a tangent line best mimics the function at a specific point. In fact, it doesn't matter if the graph intersects the line many times in a wider view. The important thing is what actually happens locally. As for the velocity, if we have information about the position, we can find the average velocity between 2 points in time. But if we take intervals to be smaller and smaller, we can find the instantaneous velocity. In the second section, we will discuss limits. We can look at limits from a numerical point of view or a graphical point of view. The idea behind a limit is to find out what happens around a point and not exactly at that point. It is possible to have a hole in your graph and you can still have a limit that exists. We introduce limits approaching from the left or the right side. The left side limit says that we are approaching the point from the negative side, while the right side is coming from the positive side. If the two one-sided limits exist and are equal, then we can say the limit exists. For example, in this graph, it shows that the limit as x approaches 2 does not exist, because the two one-sided limits are not the same. On the other hand, at x equals 5, although there seems to be a hole in the graph, the limit still exists because the limit from the left agrees with the limit from the right. We will also look at times when the limit gets large. We say that the function is unbounded and assign a negative or positive infinity. Here are the possible scenarios for vertical asymptotes. In section 2.3, we will approach limits from a symbolic point of view. We begin by establishing limits for some basic functions and use some limit laws for more complicated functions. We will also briefly cover a special theorem called the squeeze theorem. This says that if you have functions that fall between two other functions with the same limit, then the function will also have the same limit at that point. In higher mathematics, the idea of a limit hinges on looking at a function from an infinitesimal point of view. It states that for some small value, call it epsilon, can you find a value for delta so that if you are within some delta distance of your x value, you'll be guaranteed to be within epsilon of your limit. This does get a little deeper into higher mathematics, so we won't stress this too much in our class. Graphically, we think about continuity as drawing a graph without lifting your pen. In section 2.5, we will use 3 criteria to determine continuity. One is to make sure that the point is actually defined in the graph. If you don't have a y value, the limit may exist, but it's not continuous because it is not defined. A second is to make sure that the limit exists. If your one-sided limits do not agree, then the limit does not exist and therefore your function is not continuous. Finally, if the point is defined and the limit exists, then those two values have to be equal. If not, then it is not continuous. Section 2.6 discusses limits as your x values goes off to infinity. As x gets large and your graph seems to settle on a particular y value, then you can have a horizontal asymptote. This concept is sometimes known as the long-term behavior. Now, another myth about horizontal asymptotes is that it is a line that a graph approaches but never touches. As we can see here, a graph can intersect the horizontal asymptote an infinite number of times. In section 2.7, we finally get to use our limits as a tool to be able to find tangent lines. We also relate this velocity problem that we saw in the beginning of the chapter. We see that these ideas express the same concept. This is what we will call the derivative of a function. The derivative is defined to be a limit, the difference between y values divided by the difference between corresponding x values. We can see the two different forms of this quantity. Taking one of the limit expressions, we can find a derivative not just a particular number a, but if we generalize this by replacing the specific point a to a general variable x, then we can define a derivative function. This formula will be our key to finding and establishing derivatives and derivative rules. In the next chapter, we will tediously establish derivative formulas of certain functions and combinations of functions. Once we do this, we can move to take shortcuts for derivatives. Good luck!